Hello everybody. Today we're going to talk about end behavior of a polynomial function. So the first thing we need to do is we need to talk about what happens to f of x. We might refer to that as y, or the output of a function, as x, or our input, approaches negative infinity or positive infinity. All right. So like for example, I'm just going to draw a random polynomial and the details don't matter here, okay? What I don't care about on this polynomial is all of this stuff. End behavior is all about the long term. All right, it's all about the long term. I don't really care about the middle behavior. I care about the end behavior, all right? And so what I'm looking at here is, like, for example, like if I'm thinking about money in a certain stock, right? I don't really care if it loses money at first, and then I care if it gains money in the long term. So end behavior is about those long-term outcomes and how to express them mathematically. So here, for example, as we go right, the function goes down. As we go left, the function goes down. So here, I would say, end behavior is always expressed in two statements. That as x approaches negative infinity, f of x, or the output, also goes to negative infinity. Because as I go left, as I go towards negative infinity on the x-axis, my function goes down on the y-axis. As I go further left along my curve, eventually I just start going down forever. And as x approaches positive infinity, f of x also approaches negative infinity. The further right I go, at first I go up, but then I suddenly take this downturn, right? And go down forever. So it's, in the long run, both sides of this function are going towards negative infinity. That's great, but we can tell the end behavior of a function without seeing its graph. We can kind of infer what the graph looks like just by knowing two things. We just need to know its degree and the leading coefficient. Before we fill in this chart, I do just want to kind of give you an explanation as to why. If I have an even degree, right? So x squared, x to the fourth, x to the sixth, etc., right? That x squared is a negative times a negative, let's say. That's going to end up positive. X to the fourth is going to be 4 negatives times each other, and they'll all cancel out, so that's going to be positive. And same thing with x to the sixth, right? Any even amount of exponent, the negatives cancel out. So I like to think of it like that my arrows will be on the same side. They'll be even. That's always positive. And then it flips upside down if it has a negative leading coefficient or a negative a value. We might remember that from when we talked about the concavity of a parabola. If I have an odd degree, so I have x to the third, let's say. So these two negatives cancel out, and I still have one negative left over. And we can imagine this repeating itself, right? If I had x to the fifth, these two cancel out, these two cancel out, I still have that one left over, so it's negative. So I'm always going to have one end going down, one end going up. They're going to be opposite. So even degrees, they even out. It's even on both sides. Odd degree, it's a little bit weird. It's uneven, so they're going different ways. And positive numbers cubed are positive, right? So it ends positive if it's a positive leading coefficient, and it ends negative. It flips upside down if it's a negative leading coefficient. So when I'm filling in this chart, we can kind of imagine that an even degree with a positive leading coefficient, we don't know what the middle looks like, but it's going to squiggle around, maybe, and both ends point up. With a negative leading coefficient, it would just flip upside down, right? We don't really know what it does in the middle. It can squiggle around, but both ends will end up pointing down. odd degree, positive leading coefficient. It ends positive. The other one has to be going the other way because it's odd, and then they connect somehow with some squiggles. Same idea here. It ends negative. Therefore, the other end is positive because they always have to match like that. They have to be different because it's odd. And there's some squiggles in the middle, but they connect. So if I'm looking to write the end behavior of any of these four graphs, it doesn't even matter what the graph actually looks like. We really only need to know the degree and the leading coefficient. So as x approaches negative infinity here, as I go left on the graph, I end up going up. So f of x approaches positive infinity. And as x approaches positive infinity, f of x approaches positive infinity as well. It's the further right I go on the graph, the further up I go. So you should always have your x statements be the same. Negative infinity and positive infinity. One for each arrow on the graph. One for the left arrow, one for the right arrow. And then you determine whether it's going up or down at that arrow. So at the left arrow, I'm going down, so it's negative infinity. At the right arrow, I'm going down, so it's negative infinity. So on this one, the further left I go, the graph goes down, negative infinity. The further right I go, the graph goes up, positive infinity. All right, the further left I go, the graph goes up. So as x approaches negative infinity, f of x approaches positive infinity. The further right I go, the more down the graph goes. So as x approaches positive infinity, f of x approaches negative infinity. Thanks, guys. Have a great day.